Hello, Jerry Ritchie with Budzar Industries here again. Today we are in eastern Iowa at another self-contained R290 propane process system. It's a self-contained system, and we are going to be talking about maintenance and operation today. Okay, here we are on the outside of our process container system. Inside the container we have 3 independent chiller circuits. On top, we have our tower pump system, our tower fan system, and our process pump systems. To quickly go through everything, these are our exhaust fans. Because of the R290 propane, the system constantly has airflow from one end to the other. It also could be used for heating and cooling. The container's temperature controlled. When we get an alarm system, we have an audible and visual alarm system. Very obnoxious. You can hear it a mile away. If we have a problem, everybody will know. We have our hazard placard, letting anybody know that the hazards involved inside the container. We have instrument air for our pneumatic valves and our purge systems. And we also have a maintenance tap. This is our PSV, process safety valve exhaust port. In the event that we did have PSV burst, all of them are piped to this exhaust vent out to the atmosphere into a safe location. These are our process glycol headers. We are using 25% ethylene glycol for this process, and it circulates through the evaporators and then out to the process, then back to the return, and this is the closed loop system. Each has independent isolation valves for maintenance, troubleshooting, things of this nature. They all can be isolated, similar to the pumps, the tower pumps on the roof. At this time, the insulation crew is not finished. So right now, some of the pipes are still exposed, but it gives us the opportunity to see the heat trace. All of our water system, the tower system, the chemical feed system, the fill lines, everything is protected by heat trace and will be covered by insulation. We are in eastern Iowa, and it does get quite cold in the winters, so we have all this protected, but it's just not 100% complete. We are still in the startup phase. Right here, this is another example of the heat trace. This is one of the end caps. This is the heat trace. I can actually feel that it's warm. They are on and being utilized right now. They're just not covered in insulation. Then you can see the indicator at the other end of the heat trace has a light saying that it is powered, it's energized. If the light is off, the heat trace is not energized. These smaller lines here, 3/4 inch black pipe, that's for the chemical feed. The customer here is responsible for treating the tower water and keeping that in good condition. They monitor pH and just keep the water in good condition so we don't foul the towers and keep everything efficient. This enclosure is dedicated for the process pumps. Inside here, there's an enclosure heater, there's contactors, and a small I/O rack for the instrumentation. Each pump, similar to the pumps up above, can be isolated by butterfly valves, and each has a disconnect. So I can lock this motor out safely. I can put the lotto on here, and I can safely work on this pump. It's got an independent drain, isolation valves, and we could maintain this pump and utilize the other 2 and keep the process up and running. Each process pump, glycol pump, is designed for 483 gallons per minute at 50 PSI. Each pump supports the independent circuit. For example, this is chiller pump 1, chiller pump 2, chiller pump 3 down at the end. Each one is designed equally for the same flow rate and pressure. Okay, just like the enclosures inside the container, this enclosure is also protected by the Z-Purge panel made by Expo. This is where the instrument air comes in. This is where we set the air pressure, air flow. And then on this side, we have an exhaust port that has a specifically sized orifice plate to allow a certain amount of airflow through the cabinet. And then we have a relief valve. The purpose of this is to keep any arcing or flashing, any sparks away from the propane in the event of a possible leak. Up above here, we have 3 independent Marley XP MD model tower systems. We have a fill line that's covered by the insulation and the heat trace. That is complete so far. or at this point. We have an overflow line and a drain line. The drain header goes back into the building into a sump pump. We have, each basin has an electric heater. It's 6 kW and it keeps the water from freezing when the system is not in use or off. It keeps the water warm and doesn't allow it to ice up and freeze the basin and restrict flow. Each one has a isolated disconnect, so you could turn off the power and maintain or work on the system for troubleshooting purposes or for routine maintenance. They are controlled by a temperature element that is set for 45 degrees Fahrenheit. So in the event that the tower system is not in use or off, if the water gets below 45 degrees, the heater is enabled at that point and stays on until the temperature comes above 45 or is in use. Okay, each circuit, as I stated, each one is an independent chiller circuit. And when we enable circuit 1, 2, or 3, we have a block valve. So when we initiate the start sequence, the block valve opens to that particular evaporator and we circulate through that evaporator. We can run all 3 circuits at the same time, but the block valve has to be enabled and it's all in a 1-button start and stop sequence. Okay, we've come up to the top of the container system. This is where we house our tower system, including the process pumps, the tower fans, and the control enclosure. If we come around here to the back side, this particular system has 3 individual chiller circuits. Chiller 1, Chiller 2, Chiller 3. We have 3 dedicated tower pumps and a standby pump. So we have tower pump 1, 2, 3, and the 4th one is a standby pump. In case one system goes down, it can be totally isolated by manipulating these butterfly valves here, and the pump can be isolated. You just simply lock out the 3-phase power, and you can drain the system right here and work on one pump while the system continues to run without any downtime. If you look here, all the piping is protected by heat trace. The heat trace is enabled, but the installation is incomplete at the time. This is all in the works. It's a construction site still for another week or so before we turn this over to the customer for production. Okay, each individual pump, as I stated, can be isolated with the butterfly valves. Each one has a pressure transmitter, so we can see the pressure and flow rate displayed on the HMI down inside the container, the control panel. We have temperature elements that control the heat trace. You don't need the heat trace in the warmer temperature. I believe we're going to have this set to turn on around 40 degrees Fahrenheit, and the heat trace will be underneath the insulation to keep the pipes from freezing in the inclement cold weather. Okay, inside the control panel here for the tower system, we control each pump with a variable frequency drive. And this is how we control the water going through each condenser. Rather than using tower fans to reduce and accelerate the capacity control, we're using the VFD to control the water being circulated through each condenser. Okay, now we are up on top of the Marley SPX MD model towers. Once again, we have 3 individual cooling towers, 1 for each chiller circuit, but in this case, the return water is in series. So when we're running one chiller, we actually circulate water through all 3 towers, and then they can stage up based on the VFD flow rates and depending on which circuits are energized or in operation at the time. Each circuit is protected by a mechanical vibration switch. We have this in series with the overload. So if the system was to get a fault at the HMI, we have a message telling you that, to inspect the mechanical vibration switch or the motor overload. Up here, there's a couple maintenance items I need to identify. One is the grease fittings. The cooling fan motor, the shivs are inside here and they require grease periodically. We'll have to refer to the owner's manual, but I would say every couple months we'd have to grease these fittings. And there's 2 fittings right here. Then, if we lift this cover, this is where the tension is. This is where we can adjust the tension of the belts. Right now I have these set right to the factory specs, and then down below you have the pulley systems where you adjust the tension. It's on a screw to where you could basically pull the motor back farther and increase tension, or push the motor forward and decrease tension. Okay, there is an access panel to where if you needed to, you could get access to the pulley shifts inside, or to inspect the fan or the filter media. I'm going to open this door so you can see inside. That's basically what the inside of the cooling tower. Okay, one thing I want to point out is you can't see it, or it's not accessible from here without pulling the filter media. But inside here, if we were to lift this filter media, underneath here is a spray nozzle header. I believe it's 3-inch diameter, and there's a series of spray nozzles which spray the water equally around the tower system, and the fan draws the air across and cools the water to then in return cool the water circulating through our refrigerant condenser. Okay, this is the main control panel for the entire system. In this enclosure we have our HMI, which is our touchscreen panel where we can maneuver and see the status of the system. We could operate things in manual control. We could access the PID tuning blocks. It's very versatile and very useful for this application. We have a high voltage disconnect for safety. It's lockable. You can put your lotto on here. We have an e-stop. All the enclosures have e-stops. We have control power on and off. We can turn the container lights on and off. And we have our e-stop reset. Anytime there's a power interruption or you utilize an e-stop, you have to hit the e-stop reset and acknowledge the alarm here at the HMI. We have our data tag. This is very useful information. This basically is a quick overview of the system design, the process fluid, the refrigerant, the weight of the refrigerant charge, and some of our warning and safety labels. Down here in the bottom is our short version of our spare parts list. This is very useful for the customer to order spare parts or to order parts in the event of a failure. On the top here we have another one of our alarm beacons. This is the visual alarm. The audible alarms are outside in the container. Everything is utilizing EY conduit fittings. Because of the purge panel system and the volatility of the propane, every enclosure has a purge system at 1 inch of water column. Inside here, this cabinet is energized, so we're going to be very safe, of course. We have our e-stop safety switch, our Ethernet switch, and this is the brain of the system. This is our Siemens PLC processor, and it has a set of I/O racks for inputs and outputs, RTDs, things of this nature. Most of the cabinet is 24 volt DC, the blue and white and blue wire. We have a little bit of 120 in here. This is our main disconnect. This is our 3-phase 460 volt power. And we have a couple transformers. Our main transformer going from 460 volts 3-phase to single phase 120 volt. And then we have another knockdown transformer where we go from 3-phase 460 to 24 volt DC. As you can see, we have a number of fuses. Just about everything is fuse protected. And again, another safety disconnect switch, lockable from the outside. Over here, we have our temperature sensor, a PT100 3-wire RTD. This measures the ambient temperature inside the cabinet for our heater control. These are also explosion proof because of the volatility of the propane. And we have 3 of these located in the container to maintain warm temperature. We have them set for about 65, 70 degrees Fahrenheit. This is our air regulator for the purge systems and for the block valves on the process loop that we reviewed earlier. Down below are our 2 exhaust fans. The one on the left runs just about 100% of the time. We have a cross flow. On the other side of the container, we have intake vents. So this fan is running and taking air from inside the container, exiting it outside, and we're bringing air in on the other corner. The other fan is utilized in the event of a propane leak. We have an LEL propane leak detection system, very nice system, and if that is tripped or senses propane, then the second fan comes on and we increase the flow through the container for safety. Okay, this is our HMI, or some people like to refer to it as HIM, Human Interface Module. This is basically the control center. This is where we start and stop the system. We can monitor the system, each circuit individually, and it's a one-button start and stop. It's programmed and designed, very simple operation, just one button start and stop. We have 3 individual circuits. They can be displayed, and when the system is running, we turned it off so we could do the recording and the video, but you can see there's a lot of useful information on this screen. We can monitor superheat, subcooling, process temperatures, flow rates, the pump on, off, compressor on, off, whether it's loaded, unloaded. There's a lot of information on here that's great to just monitor the system and maintain good performance, or for troubleshooting purposes. If there was something wrong, or it's very useful information, and we could go to each circuit or each chiller. Now we're at chiller 2, chiller 3, and then we also have the rooftop system where for the tower system. Again, we have 3 pumps, 1 for each chiller, and then a standby pump. On this screen, you could select each tower, and we also have a cycling parameters. This is what controls when the fans cycle on and off, at which temperatures they come on and off. We have a safety screen. This is all of our program safeties. These are also noted on our schematics for reference, but they're also saved here. We have alarm history. We could see a history of alarms. Right now there's quite a few alarms because we're still in the startup and testing phase. The system has not been turned over to the customer quite yet. Back to the chiller screens. We have a lot of information here, and we have our alarm indicator. Right now we have a couple alarms just because our purge systems are not being utilized, again, because we're recording and filming. But if you hit the alarm button, you get your active alarm screen. And we programmed a one-button acknowledge all. So in the event of an alarm, once you address the problem or correct the problem, then you just hit acknowledge all, and the alarms, in the event that they are cleared or the problem is no longer active, the alarm will acknowledge and clear, and you reset basically. This KPI button is the number of starts and compressor run hours for each circuit. For example, right now we're on chiller 1 KPI. Now this has been reset a couple times during our testing back at home for our factory acceptance test. But for example, I could go to chiller 2, we're now at chiller 2, and I press KPI, and it gives me the compressor starts and compressor run hours for that individual circuit. Okay, now for troubleshooting purposes, or I'll be utilizing these buttons here soon when we run the system and do further tuning, but I can tune, for example, the electronic expansion valve. It has our superheat set point of 12 degrees Fahrenheit, and this is my PID tuning block, and I also have a manual function. I can open and close this valve to any position I want based on a percentage on the 4 to 20 milliamp loop. It's also programmed pretty creatively. Our programming team and engineering team did a really nice job with the graphics, and I can do the same thing to tune the variable frequency drives, VFDs, for the tower pump systems. Each one has its own tuning block. This also can be used for manual function or troubleshooting purposes. This is one of 3 high voltage cabinets for each chiller circuit. Again, has a isolated disconnect handle that's lockable for LOTO. If we open these up, you can see inside, this is our incoming power from the service box outside. We have a 460 to 120 volt transformer. We have our phase monitor. This detects any phase imbalance, the difference between the different legs. And then we have our compressor motor protector, CMP. This is directly related to the screw compressors. The compressors are fuse protected for the 300 horsepower screw Frostgold compressors. And then we have a little bit of control wire here that goes to another enclosure we'll touch base on here in a minute. Each chiller has a high voltage cabinet, which we already covered, but that also has a control cabinet. Inside this cabinet is the PLC I/O rack, which communicates with the main enclosure, which we covered earlier. It has its own power switch and power indicating light. Each control panel has a Siemens ET200S model I/O rack. This has all our inputs and outputs and all of our temperature and pressure sensors. These all go back to the main control panel where the HMI is located. These are Danfoss superheat control boards. These controllers control our electronic expansion valves for our refrigerant flow through the evaporator. We have a series of relays, and everything in this cabinet is 24 volt DC. It's all safe and easy to maintain and troubleshoot. Everything's labeled, everything's identified. Each one of these enclosures also has a purge system at 1-inch water column to keep all the electronic components separate from the propane. Okay, now we're going to talk about the propane leak detection system. In this application, we're using a Draguard device. This is located right here. It is located low because the propane is heavier than air. This is an LEL, low explosion limit sensor. We have it programmed for 50 ppm. If the propane in the container reaches 50 parts per million or higher, it's displayed here on the digital display, and this is what triggers the alarm. The audible and visual alarms throughout the container and outside of the container. This is a very important instrument for this system. In the event that we do have a propane leak and trips the LEL propane sensor, it will trigger all the alarms, but as the ventilation system triggers and we move the refrigerant out of the container, the LEL display will reduce. Once it goes back down to 0, you have to use a magnet, because it's an explosion-proof device, to reset the device. You simply place the magnet by the OK button. It will reset the device locally, and then you go to the HMI in the main control panel and acknowledge the alarm there as well. That will shut off all the audible and visual alarms, and you'll be able to go back to running. Okay, now we're going to talk about the refrigerant circuit and each individual chiller in more detail. We have a Frostgold screw compressor. It's actually a twin screw compressor. Then we go into the water-cooled condenser. We condense the high pressure, high temperature gas to a liquid. We come down to our liquid line. This is it here. Throughout the refrigerant circuit, we have plenty of isolation valves for maintenance and for repairs. The liquid line goes down here. Again, we have some more service valves for pressure gauges, things of this nature, pulling a vacuum, evacuating the system, several uses for the service valves. Then we have our liquid filters. We have our liquid line solenoids. Again, a couple more service valves for pressure gauges. And then we go into the electronic expansion valves. These are controlled by the Danfoss control boards in the control panel. And they have little sight glasses, and as usual, you're looking for a green indicator for a nice dry system. Then it goes, this is our hot gas bypass lines. We have capacity control. We unload full capacity, 25 to 100%, and we have hot gas bypass also for capacity control. This is our shell and tube evaporator. It's a dual circuit evaporator. This is the glycol comes in one side and comes out cold on the other. This is where the cooling or chilling is done. This system is designed for 20 degrees Fahrenheit, leaving fluid temperature. Okay, one of the key features of our refrigerant circuit is our three-way pressure safety assemblies. We have a three-way valve where the one connection is connected to the refrigerant circuit, and then we have a valve where we can isolate each pressure safety valve. Each pressure safety valve also has a rupture disc, then a pressure transmitter chamber, and then the PSV. The reason for this is we want to know if the pressure increases before the safety valve releases or pops. So in this case, if we see pressure in this chamber, we will shut down the system and you'll get an alarm at the HMI, the lights will go off, and we can address the situation before the pressure safety valve releases and we lose propane to the atmosphere. Okay, this is our tower water piping. We monitor temperature in and out, PT100 RTDs. It's also protected by 150 PSI pressure safety valve, PSV. And that if that was ever to release, it has a blow down tube and goes to our stainless steel drip pans. The entire chiller, each circuit, each chiller is self-contained, and in the event of a glycol leak or a tower water leak, it collects in the drip pans in the bottom, and at the end of the drip pan there's a 1/2-inch drain connection. We also monitor evaporator inlet and outlet temperature, again with a PT100 RTD in a thermal well, so they could be removed and taken out for calibration or replacement or service without draining the system. Okay, this is our differential pressure transmitter. Basically, we have a tube going to the evaporator inlet and outlet, and we display the PSID, pressure difference across the evaporator. This is basically our flow acknowledgement. This is also displayed at the HMI and the main control panel. Anytime the system is drained or refilled or isolated for service or maintenance, we have the vent tubes here. Each tube, you get a small wrench and turn this counterclockwise, and there's a weep hole to vent the air out of the pressure differential transmitter. Okay, here we are at the back end of our container system, and these are the biometric dampers. When the fan is running, these open basically to the level of airflow being moved through the container. When one fan is on, it opens slightly. When both fans are on, it opens more, allowing more circulation and airflow through the container. This is circuit 3, the farthest one. We're moving back towards circuit 2. Again, they're completely identical circuits, except circuit 1 has the LEL propane leak detection system. Each has a main cabinet, control cabinet, and we go all the way back to circuit or chiller 1. This concludes our maintenance review of the systems. Thank you for your time, and please refer to the owner's manual or maintenance manual for further details. The manual includes data sheets or cut sheets for every single component, whether it's electrical or mechanical. Our manual is assembled by our engineering department, and it is very useful, very helpful.